Addition of carbon nucleophiles to carbonyl carbon. Terminal alkynes, when they react with a strong base such as NaNH2, it's going to give us acetylide ion. Acetylide ion is another carbon nucleophile which can add to the carbon oxygen double bond of aldehydes and ketones. So this acetylide ion can go and make a nucleophilic attack on this carbon, thrust these electrons onto oxygen to form the tetrahedral intermediate. Now, once the tetrahedral intermediate is obtained, a weak acid such as pyridinium ion will be added to the reaction mixture to protonate the alkoxide ion. Here is the structure for pyridinium ion. And this alkoxide ion is going to grab this hydrogen, neutralize this positive charge on pyridine to give us the nucleophilic addition product. So as you can see from here, here is the new carbon-carbon bond that has been formed. This is the new carbon-carbon bond that has been formed. And this is the nucleophilic addition product. Apart from Grignard reagent and acetylide ion, we can also use cyanide ion as a carbon nucleophile to get added to the carbon-oxygen double bond of aldehydes and ketones. Now, the nucleophilic addition product that will be obtained is generally called as a cyanohydrin in this case, where the cyanide group and the hydroxy group are present on the same carbon. Now, this particular reaction is conducted under acidic conditions, and you will see why we are using acid in this reaction when we look into the mechanism. And also, when we are using acid, this acid might protonate the CN-, right? So that is the reason we wanted to take excess of cyanide ion, so we can make sure that we have enough cyanide ion for the nucleophilic attack on the carbonyl carbon. Let's now take a look into the mechanism. First, to begin with, the CN- is going to make a nucleophilic attack on this carbon, electrophilic carbon, to thrust these electrons onto oxygen. So this is going to give us a tetrahedral intermediate. Let's draw the structure for the tetrahedral intermediate. So this is how it's going to look like. Now, in the next step, this alkoxide ion will be protonated by the undissociated HCN molecule. So how did we get the undissociated HCl molecule? Because we did have enough proton in here. We did have enough acid in here. That's going to make sure that we have enough HCN, right? So where these electrons from the oxygen is going to go grab this hydrogen, and the CN- is going to leave. When compared with Grignard reagents and acetylide ion, the CN- is a relatively weak base. Because when you take a look into the carbon nucleophile Grignard reagent, let's take this Grignard reagent. Here the carbon nucleophile would be this, right? And the conjugate acid of this is going to be ethane molecule, right? Which has a pK value greater than 60. In the case of acetylide ion, right? Acetylene molecule is the conjugate acid. So this one right here is a conjugate acid, right? Which has a pK value of approximately 25. Let's do the same thing for cyanide ion. And the conjugate acid is going to be HCN, but this one has a pK value of close to pK value of 9.14. Now, since this is the strongest acid in all of this, okay, the conjugate base should be a weaker base. So this one should be a weaker base. Since CN- is a weaker base, it can get eliminated from the nucleophilic addition product. But this is not going to happen under normal conditions because cyanohydrin in general is a stable compound. Because this OH is not going to put these electrons in here to form the double bond to kick off the CN. Because if it's going to do that, then this is going to have a partial positive charge on it, which is going to lead to an unstable transition state. So how the CN- is going to leave from the system? The CN- can leave from the system if this hydrogen is deprotonated first. Now let's see how this is going to happen. So let's say that you are going to react the cyanohydrin under basic conditions. So under basic conditions, this OH- is going to go grab this hydrogen, and there will be negative charge on this oxygen, right? So this oxygen will now have negative charge on it. This would be the intermediate that will be formed. Now, in this case, the oxygen can push these electrons in to form the double bond and now thrust out the Cn minus. You can see that the Cn minus is getting eliminated. So in which case the original compound has been reformed. So what we have concluded here is cyanide ion can react with aldehydes and ketones to give us cyanohydrins, but the cyanohydrins can be converted back into the aldehyde and ketone if they are going to be in the basic medium where this hydrogen will be deprotonated. Okay, so here is the aldehyde or ketone that will be formed. The addition of cyanide ion to aldehydes and ketones to form cyanohydrin is a useful reaction because from cyanohydrin we can get number of useful products. Say for example, when cyanohydrin is heated in the presence of acid, it's going to get converted into carboxylic acid. So this part right here is going to get converted into carboxylic acid. This is an hydrolysis reaction. So the product here would look like this. And the cyanohydrin can also be reduced where it reacts with two molecules of hydrogen in the presence of Raney nickel, in which case these two atoms will get saturated with hydrogen. So the product would be a primary amine here in this case.